The wildfire did not just make smoke, it built a thunderstorm. On August 2nd, 2026, NASA's Terra satellite watched Utah's Widemouth 2 fire produce 2 towering bursts. The thermal view exposes the real clue: cloud tops colder than -40 degrees Celsius. That is the signature of air rising fast enough to reach the upper troposphere. This kind of storm is called a pyrocumulonimbus, or pyro. Heat from an intense fire drives air upward. Water vapor condenses, the column strengthens, builds ice, and can produce lightning. But NASA's new INSPYRE campaign is chasing a harder question. Which fire clouds stop in ordinary weather, and which ones inject smoke much higher? The Widemouth event gave researchers a useful test. The first pulse appeared near midday. A second pulse formed later that afternoon. By the next day, the active storm was gone, but its transported smoke remained. A research aircraft sampled that drifting plume near 12 kilometers above the ground. The aircraft did not fly through the storm core. It intercepted the smoke after winds had carried it away. That altitude is the important evidence. The lower atmosphere is constantly mixed and washed by weather. The stratosphere is different. It is mostly dry and cloudless. Smoke that reaches it can spread across enormous distances and, after sufficiently large events, persist for months or even years. That does not mean this Utah fire changed the global climate. NASA described the Widemouth pyroc as relatively routine and minor. The value of the event was access. Researchers could compare satellite temperatures, the storm's timing, weather observations, and direct measurements inside the transported plume. Those measurements help answer 4 connected questions. What fire intensity is needed to build a pyroc? What weather lets the column keep rising? How much smoke crosses into the stratosphere? And once it gets there, how does it change atmospheric chemistry and Earth's radiation budget? The last question matters, because smoke contains particles that absorb and scatter sunlight. Scientists are still working out how those effects scale from one event to the largest fire cloud outbreaks. There is also a forecasting problem. Satellites can see a plume grow. Radar and lightning networks can watch the storm organize. Aircraft can sample the aftermath. But emergency managers need warning before the column crosses the critical boundary. Widemouth 2 was not the giant disaster. It was the rehearsal. 2 satellite pulses, 1 plume sampled near 12 kilometers, and a chance to connect the fire on the ground with the chemistry above the weather. The next major pyroc knot may leave a much larger atmospheric fingerprint. The question is whether scientists can recognize that transition while the storm is still building.